Hi everyone, this video is about how to do problems with energy density and specific energy. So I'll start with a quick introduction to energy content of fuels. So all fuels contain a certain amount of energy, typically as chemical potential energy, or in the case of uranium, as nuclear potential energy. And this can be measured as energy per liter, per volume, or per kilogram, which is per mass. In that case, we actually give energy content two different names. If you're measuring per volume, we call it energy density. The units are going to be megajoules per liter or megajoules per meter cubed. And I'll talk in a second. Liters and meter cubes are not the same at all. In fact, there's 1,000 liters per meter cube. Specific energy is the term we use when we're saying energy per mass. And so that's usually going to be megajoules per kilogram. Now, I will say that some of my old worksheets, and I kind of have a bad habit of using the phrase energy density for everything, for both energy density and specific energy, but I'll try to be really clear and use the correct term in the right place. But some of the old worksheets that I made may just say energy density. Okay, so when we're looking at energy content of fuels, for example, you might be talking about coal or gasoline, straight oil, wood, or uranium. And the thing is that like a tiny bit of uranium can have the same amount of energy as a ton of coal. Here's a slide that shows just this little 7 grams of uranium has such an incredible energy content that the energy release would be the same as releasing the energy from a ton of coal. And a ton is 2,000 pounds. So it's a pretty significant difference in energy density. Now, you are not expected to memorize energy densities and specific energies. Page 311 of your textbook is going to have a list. Let me write that here for you. And you probably noticed it when you've been taking notes. So page 311 of the yellow IB textbook is going to have a list of energy densities and specific energies. Here's another list I pulled off the web. There's plenty of lists of these, and they may vary, but because you're not expected to memorize these, an IB question is typically going to just give you and say, use this energy density or specific energy. If you're not given one, then look it up on page 311 of the yellow textbook. So just a real quick note, this is something you can refer back to. Again, megajoules per liter, megajoules per meter cube is not the same. A liter is tiny, so it takes 1,000 liters to equal a meter cubed. So then the energy densities or specific energy is reversed. When you have 1,000 megajoules in a meter cubed is equal to 1 megajoule per liter. When do we use specific energy as opposed to energy density? And it's typically things that are liquids or gases, really especially for things that are gases, like natural gas. They're going to be reported as energy per volume, and you'll often see like a pressure written next to it because the volume of a gas will change with pressure. Energy content for solid things like coal and wood and nuclear fuels are usually going to be energies per mass, but you should be able to use either. Alrighty, so the tricky thing about solving specific energy and energy density problems is that there's no formal equations for it. If you've looked in the IB data booklet, they don't have any equations for it, and they don't even have any specific symbols for it. Now, some textbooks I've seen will use an E subscript D to mean energy density. The only thing I don't like about that is it makes it look like it's a type of energy and that the units would be joules or megajoules, but they're not. Remember, if it's an energy density, it's going to be like a megajoule per liter or meter cubed. And then sometimes they'll use ES for specific energy, and then they're talking about megajoules per kilogram. In some of my worksheets, you'll see me use like ED for energy density, SEs for specific energy, but ultimately it doesn't matter. Use what works for you. Okay, so in that sense, and actually let me go back and see if I can erase that writing I put over that. Okay, here you go. So you could create an equation though. So energy density, you could say is E over V, energy over volume, and specific energy is SE E over M. So in the equations that you're gonna see on the next couple pages, you're just gonna see me use ED equals E over V and SC equals E over M. Again, you can write the equations the way you would like to. All right, so here's sample problem number one. The specific energy of oil is 44 megajoules per kilogram. And we want to know how much energy, chemical potential energy, is contained in 928 kilograms of oil. Now, notice that they're not saying energy produced in the form of electricity or kinetic energy, because that involves a whole nother step, including efficiencies. And right now, we're not going to worry about efficiencies. Let's just keep the problem simple, and then we'll add efficiencies in. Okay, so there's our givens, our specific energy, our mass, and we want to figure out how much energy is contained in there. We'll use our equation. Specific energy is energy over mass. We'll rearrange it algebraically. Energy is mass times specific energy, and we're going to plug in our numbers. Do the math, and we'll get 40,832 megajoules. But I want you to go back, and one of the most important things about doing any of these kind of equations, problems for energy production is be really, really careful with the unit analysis. Unit analysis, paying attention to units and canceling them, is really the best tool you're going to have. So go back and be really careful. Kilograms cancel. What units are you left with? You're left with megajoules, and that's what you wanted. So because you're left with a unit of energy, you know you basically set it up correctly. Okay? I always like to put things in simple units. I turned it into 41 gigajoules. You don't have to, but you certainly can if you want. All right? Remember, stop and replay the video as you need to, going through those problems. On the next slide, I'm actually going to do the same problem, but I'm not going to set it up the way we traditionally would. Of course, I always prefer that you set things up super carefully, but because there are no equations given by IB for these kind of problems, again, unit analysis is going to be your friend. So if you're stuck when you're trying to solve these problems, just think about the units. In this problem, they want us to solve for energy. So I know I've got to come out in the end with some sort of unit of energy. I'm going to start with whatever of my givens contains energy in the numerator. So here, 44 megajoules per kilogram, I've got megajoules in my numerator. To get rid of kilograms, I'm going to multiply by my mass, and I end up with the units I want. So here's a way, and honestly, it's how I got through a lot of my engineering classes in college, is just doing unit analysis. Of course, try to set things up. You still want to write down all of your givens and so forth, but being able to just look at the units can really help you a lot. Okay, let's go on to another problem. Sample problem number two. Again, we're going to ignore efficiency at this time, and we will come back and add efficiency in because it just gets a teeny bit more complicated. All right, a natural gas plant produced 85 megajoules of energy. The energy density of natural gas is 41 megajoules per meter cubed. What volume of natural gas was burned? And again, we're just going to assume the efficiency is 100%. We know our energy density, and we know the energy that was produced. We want to find the volume. The equation for energy density is energy divided by volume, and we're just going to rearrange that algebraically. For volume is energy divided by energy density. Be careful with your algebra. That's going to be a big key to these problems. And we'll just go ahead and plug in our energy and our energy density. This is where again, you're going to want to be really careful canceling units. You've got megajoules on top, megajoules on the bottom, and you're left with 1 over 1 over meter cubed. And so 1 over 1 over meter cubed equals a meter cubed. So your units in the end actually turn out to be meters cubed. So you've got 85 divided by 41, 2.1 meters cubed. I think you guys will be just fine with that part. Alrighty, so let's move on and let's look at problems where we combine efficiency with these. All right, so one way of looking at this, if you prefer to have equations to work with, is you can say, well, the energy produced is your specific energy times your mass times your efficiency. You can say energy produced or energy out, and then there's an algebraic way of saying it. For energy density, same idea. You can have specific, energy density times volume times efficiency. Same form of the equation, but we're going to multiply efficiency, and now we can call it the actual energy produced. For example, if you're putting coal into a power plant, it's the electricity that you're getting out, because we're looking at the efficiency of turning the coal potential energy into electricity. Okay. All right, so here's a problem. Julian put 2.9 kilograms of gas into his generator. The efficiency is 19%. Specific energy is 45. How much energy as electricity were we able to get? And we're going to write down all of our variables and our equations. There's our equation for efficiency. And we're going to rearrange our equation for efficiency. I can actually show a couple more things here so you can see all the variables. There we go. We can rearrange our equation for efficiency to solve for energy out, because that's what we wanted. So here we have our energy out is efficiency times energy in. Now, where are we getting this energy in from? That's the key. We're getting this energy in. The energy in comes from the gasoline. So this comes from burning the gasoline, comes from burning gasoline in the generator. Okay, so we need to find that. And before, we looked at our specific energy equation as being energy divided by mass, but really this is going to be the energy that's going to go into the generator and becomes the energy in the denominator of our efficiency equation. Okay, so specific energy now becomes energy in divided by mass, and we can rearrange and solve for energy in algebraically. So now we have energy in equals specific energy times mass. All right, what do we really want though? We really wanted our energy out, so let's bring that equation down here, and we're going to plug our equation for energy in into this equation right here. So we end up with energy out is our efficiency times our specific energy times our mass. And I'm simply deriving the equation I showed you on the previous page. So that's all I'm doing. I want you to know where they're coming from so that you know how to do it yourself, because again, IB doesn't give you these equations. All right, we can plug it in and we get 25 megajoules. Again, be really careful with canceling your units. Kilograms cancels with kilograms. Efficiency doesn't have any units. That's why it gets a little trickier about where to put it, and you want to be really careful. And we're left with megajoules, which is what we wanted. All right, so don't forget to pause that and replay it however you need to. Okay, one last sample problem. Sample problem 4 is about nuclear power. So the Monticello power plant is 37% efficient. If it produces 45 gigajoules of electricity, how much uranium was consumed? And they mean how much in terms of mass. The specific energy is 8.1 times 10 to the 7 megajoules per kilogram. All right, we have our givens, our specific energy, our energy out, our efficiency, and we want to figure out the mass. So we're just going to go back to the equations I gave you 2 maybe slides ago. Energy out, specific energy times mass times efficiency. And we're going to rearrange it this time for mass. So we're just using our algebra and we're solving for mass. Kind of the reverse of the last problem you did. Plug in our numbers. Be really careful to cancel your units. And again, you've got a 1 over 1 over kilogram situation, giving you the final units of kilograms. And I put it in grams. You certainly don't have to. Okay, I hope those problems help. I will probably continue to put up sample problems like those because they are a little bit more challenging. All right, good luck. Email me if you have questions.